We now consider the center of mass of a system of particles, and this will extend later to the center mass of regular objects, solid bodies. So let's consider a spatial coordinate system y, x, and 3 particles of non-zero mass that have certain coordinates, r1, r2, and r3. These are vector positions that can be specified in terms of x and y. So that the ith vector position is xi plus yi. Now the center of mass of the system of particles is simply defined as follows. It's the product of the mass and position of each one of them added together. And then we're going to divide by the entire mass of the system of particles. So that's it. That is the position to the center of mass of this system of particles. So there it is in slightly more concise symbology. And the interpretation of this is that it is the average position of the masses, or perhaps better said, the mass-weighted average position. So it's the average position of the particles weighted by their mass. So if one of these masses is greater than the others, say R1 is more than R2 or R3, then it's going to shift the position of the center mass closer to this particle here, etc. Now for many solids, the center mass is just the geometric center. Take a bowling ball right in the center. If the density is constant, it would just be in the geometric center. If there's an axis of symmetry, the center mass lies along it. And the center mass may lie outside of the body. It doesn't actually have to reside in the material mass of the body itself. So there's a few ideas. Let's extend our position of the center mass to velocity of center mass. And note that on the previous slide, I think I conflated the position and the mass of the particles. So I said mass or particle R1, for instance. I meant M1, but you probably picked that up already. All right, velocity of center mass in the x direction is just the rate at which the position changes. dx center mass dt. And the same thing for in the y direction and z directions if it's a three-dimensional system. So it's just the derivative of the position. Therefore, the velocity of the center of mass, instead of being multiplied by the position components, it's multiplied by the velocity components and divided by the total mass as before. So m total, velocity center of mass, if we multiply this whole thing by the total mass, we get m1v1 m2v2 plus m3v3, and that's just another way to say the total momentum, mass total velocity of the center of mass. So the total momentum in any system of particles is add up all the mass and take the velocity of the center mass. That's a pretty useful concept, because if there's 1,000,000,001 particles all doing their own thing, if you know the velocity of the center mass, which is obviously not going to be real easy, you happen to know the mass total, no matter what the particles do, bouncing off each other, interacting, whatever, the velocity of the center mass is going to stay constant because the total momentum is constant. All right, and then acceleration, same idea. The derivative of the velocity in both dimensions, we can just write the acceleration of the center mass is the rate at which the velocity of the center mass changes. And so mass total times acceleration of the center mass is simply the mass of the individual object times its acceleration. So add them all up, and this gives us the sum of F, because of course sum of F is ma. And that's sum of the external forces plus the sum of the internal forces, but the sum of the internal forces always adds up to 0. So we basically just demonstrated that the sum of the forces is the rate at which the momentum changes, which you already knew. Let's use the concept of center mass to solve this problem. We have not so smart Bob and his slightly less massive, not so bright Bill having a tug of war, and they're on glare ice. All right, so they have 100 kilograms and 80 kilograms. The prize is a lovely harp that whoever gets to it first, by pulling on each other, as they pull on the rope, they're pulling on each other. They're both going to be sliding toward the harp, and they're really excited about that. See, that's more evidence that they're not so bright. But in any case, who arrives first? And where is the center mass of the system? They go hand in hand, it turns out. So the dimensions, Bob is 10 meters from the harp, and Bill is 12 meters from the harp. So it's not so obvious. You probably realize that Bill is going to accelerate more rapidly because he has less mass and the forces are equal and opposite, but yet Bob has a shorter distance to go. So it's just not immediately intuitive who's going to win, who's going to actually get the harp. So let's solve it. Let's get the position of the center of mass. So our reference point is x is equal to 0. So from here, we're going to plug it in to the center mass equation. Mass 1, we'll call that Bob, times his position, plus Bill's mass times his position over the total mass. So from x is equal to 0, we have Bob being at -10, Bill being at 12, multiplied by the respective masses, divided by the total mass, and we get the position of the center mass minus 0.22 meters. So the center mass of these two characters is somewhere right around here. Now I'm going to let you in on a little secret. It turns out that, you might expect this even, as they pull on this rope, they are going to meet at the center mass. So that tells you who wins. But we don't necessarily know that yet, so let's assume that, for sake of argument, that Bob arrives at x is equal to 0 first. Let's use the center mass equation to figure out where Bill will be if Bob is right here at the harp. So we have m, x prime m, in other words, the position of Bob after the fact is 0. He's at the harp. So let's solve for Bill's position, where the center mass is minus 0.22, so we can rewrite the equation. We have 100 times 0 plus 80 times Bill's position. So this is what we're looking for, divided by 180. So solving for x prime of Bill, we discover that he is at minus 1.745. So obviously Bill arrives first. And that's consistent with the fact that we recognize that they are going to meet here at minus 0.22. So what does Bill do with the harp? Well, I'm sure you know. It's pretty self-evident what someone not so bright would do with the harp. Let's do a momentum problem where we start with a 20 kilogram projectile fired from a 60-degree angle at 240 meters per second. So it's going to follow this parabolic path, supposedly, except when it gets to the top of its flight, this 20 kilogram mass, which would normally follow this standard path as shown here, it's going to explode. There it is, exploding. And that explosion is going to result in half of it basically being the 20 kilogram projectile is blown in half. And half of it drops straight down. And the other half is obviously given an impulse, which increases its velocity. So what's the range of the fragment that's left, which would be here, and how much energy is released during that explosion? So the object, half of the object, 10 kilograms, falls straight down after the explosion. So obviously it's given a boost. The other fragment is given a boost and it lands somewhere further on. Conservation momentum says that the fragment gets the same amount of impulse that was lost by this fragment. You could probably do that in your head since it's half of the mass. But in any case, it gets 1/2 of mvx. Now this is not energy, this is a momentum component. This is the amount that's added to the momentum of the fragment. Because this 1/2 of the total mass, which is 10 kilograms, times Vx is how much this 10 kilogram fragment lost. So the mass is 10, and that's 1/2 the total mass. And then 240 cosine of 60 is how much velocity it has in the x direction, which is all you have up at the top. So what the fragment gets is 1,200 kilogram meters per second. That's how much momentum is added to the fragment, lost by the casing or the back end. So at the top, we have Vx equals the V0 cosine of phi, the original velocity in the x direction. Now, in addition to that, we're going to add to the fragment, to this initial velocity, the momentum over mass. That's a velocity component here. It's got the dimensions of velocity. So that is 120. Basically just half of the speed, which is 240, is in the x direction with a 60-degree angle, plus the additional momentum gain divided by the mass, which gives us 240 meters per second. So you basically just doubled the speed. Well, what's the flight time? The flight time. Recognizing that the up and down time is the time up plus the time down, and the explosion doesn't change that because it only adds to the horizontal speed, and therefore the time of flight is not affected. No vertical motion has been affected. So what's the range? The range is Vx times time up and down. In this problem, we have that Vx changes. So since it increased, we have to consider that the range is going to be based on moving at 240 meters per second up at this point. So the actual range, R, is Vx1 times time up on the way up plus Vx2 times the time down. Time up and down is twice the time up, which is twice. Time up is acceleration times time is change in velocity. So the vertical velocity divided by acceleration is the time. Hopefully that makes sense. You can, again, velocity is just acceleration times time. So that's 2 times the vertical velocity is V0 sine of 60. Then we're going to divide that by g. So this gives us the total flight time. Now the range is 120 times half of that. There's half of the flight time on the way up, plus 240 times the amount of time to go down, and that gives us 7.63 kilometers total. Pretty good range there. Now how about energy? What was the change in energy as a result of the explosion? Well, it's the fragment energy, the energy it has now, minus the energy it had at the top before it exploded, because half of that mass, that 10 kilograms, was stopped dead in its tracks, so it had no energy. So the total energy of the 20 kilograms at the top, and then we're going to subtract that from the fragment energy. So the fragment energy is 1/2 the mass, so 1/2 m over 2, but the speed or the velocity is doubled, and we're going to subtract off 1/2 m Vx squared. So that just gives us mvx squared minus 1/2 mvx squared, which is 1/2 mvx squared, which is 10 times 120 squared, 144 kilojoules.